50 years ago, Stephen Hawking predicted they existed. Black holes born in the very first microsecond after the Big Bang itself. Last November, something collided 900 million light-years away. The signal reached Earth on November 12th. And when the data came back from LIGO, it showed something that weighs less than our sun. Something that, by every known process in the universe. You're listening to Stardrift FM. March 2026, 69 space stories happened this month. 69 launches, discoveries, collisions, missions, and moments that pushed at what we understand about the universe. We read all of them. We ranked 20. Starting from the bottom, number 20, working our way up to the story of the month. The one that, if the follow-up data confirms it, rewrites the first second of the universe. Grab your coffee, settle in. Here we go. Number 20. Nobody expected what NASA announced on March 24th. Administrator Jared Isaacman held an event called Ignition at NASA headquarters. Two headlines came out of it. First, NASA commits $20 to $30 billion to building a permanent moon base, not a temporary outpost, a base. 76 landings over the next decade, delivering over 200 metric tons of hardware. Habitats, nuclear power systems, rovers, drones, and in-situ manufacturing equipment on the lunar surface. Second headline, the Lunar Gateway, the planned space station in lunar orbit that's been central to the Artemis architecture for years, is scrapped. Paused in its current form, all resources redirect to the surface. And then there's SR-1 Freedom, Space Reactor 1 Freedom, the first nuclear electric propulsion spacecraft in history. It launches to Mars before the end of 2028, carrying a payload of next-generation Ingenuity-class helicopters for Martian aerial exploration. Nuclear propulsion for space has been studied since the 1960s. Programs were canceled in '72 and 2005. SR-1 Freedom is the first time it will actually fly between planets. It's number 20 because these are announcements, not achievements. The moon base is a plan. The nuclear spacecraft is a promise, but they're significant promises. Up next, number 19. On Mars, right now, something strange is growing out of the ground. From orbit, they look like giant spiderwebs etched across the Martian surface. Up close, there's something else entirely. NASA's Curiosity rover has been exploring what scientists call boxwork formations on Mount Sharp for about 6 months. Networks of mineralized ridges, 1 to 2 meters tall, taller than a person, stretching for miles across the terrain. On Earth, formations like these are typically centimeters tall. On Mars, they're massive. They form when ancient groundwater seeps through cracks in bedrock, deposits minerals, and the surrounding softer rock erodes away over billions of years. Curiosity also found something the science team can't quite explain yet: pea-sized, egg-like nodules scattered throughout the ridges and hollows. Not where the water channels were, but between them. A second episode of groundwater activity, possibly, that came after the ridges were already cemented. Here's the significance: the boxwork is unusually high up Mount Sharp. That means the ancient groundwater table was much higher than scientists previously estimated from orbital data alone. Water extended further, lasted longer. The window in which microbial life could have survived on ancient Mars may be significantly wider than previously modeled. Mission scientist Tina Seeger from Rice University. Seeing boxwork this far up the mountain suggests the groundwater table had to be pretty high. And that means the water needed for sustaining life could have lasted much longer than we thought looking from orbit. Number 19, because it deepens an existing story rather than breaking a new one. But those implications for Martian habitability are real. Next, number 18, a planet 10 light-years away just got very interesting. If you want to find a planet that could harbor life, the first thing you want is a quiet star. One that doesn't flare, doesn't blast its planets with radiation, doesn't strip away whatever atmosphere they managed to build. GJ887 is that star. 10.7 light-years away, the 12th closest planetary system to our Sun. Also the brightest M-dwarf in the entire sky. In March, a team using ESO's HERPS and ESP ERI-SO spectrographs confirmed a 4-planet system around it, including one planet sitting squarely in the habitable zone. GJ887d completes one orbit every 50 days, well within the region where liquid water could exist on its surface. Its minimum mass is 6.1 times Earth's. We don't know yet whether it's rocky or an ocean world or something in between. But the star rotates slowly, shows nearly constant brightness, and flares rarely, which means any atmosphere this planet builds stands a much better chance of surviving than it would around a more active red dwarf. For comparison, Proxima Centauri b is closer at 4 light-years, but Proxima is a violent star. GJ8887d is farther, but the stellar environment is far more hospitable. It sits on the Habitable Worlds Observatory's prime target list. Number 18 because it's a candidate, not a confirmation. But a candidate this close, around a star this calm, is worth paying attention to. Number 17. Jupiter's northern lights are doing something that no physics model predicts. Jupiter has the most powerful, most continuously active aurora in the solar system, hundreds of times brighter than Earth's northern lights. In March, JWST spotted something inside it that makes no sense. Katie Knowles, a PhD researcher at Northumbria University, used Webb's NER-SPEC instrument to observe Jupiter's northern aurora for 22 continuous hours. In one of 5 snapshots, she found a cold spot, 228 degrees cooler than the surrounding aurora, 538 Kelvin versus 766. And paradoxically, the cold region had 3 times the density of charged hydrogen ions. More particles colliding should produce more heat, that's basic physics. Something is actively cooling this region, fast enough that temperatures changed on timescales of minutes. No existing model of planetary atmospheres predicts a cold, dense patch in an otherwise hot, diffuse aurora. The cold spot sits in what's called the Io flux tube footprint, the region where approximately 1 milliamps of electric current crash into the planet's ionosphere. Io's volcanoes inject sulfur into a plasma torus around Jupiter, and that plasma drives one of the most intense auroral features in the solar system. Somehow, in the heart of all that, something is cold. This is the first time physical properties, temperature and ion density, of these auroral footprints have been measured rather than just their brightness. JWST opened a new diagnostic window and immediately found something inexplicable. Number 17, because it's beautiful and genuinely puzzling, but one observation. The follow-up campaign will tell us more. Number 16, cosmology's biggest disagreement just got a new approach. The universe is expanding, but how fast? That question has been splitting cosmologists for a decade. 2 independent measurement methods, 2 answers that won't agree. Local observations of supernovae and Cepheid stars say the universe expands at 73 kilometers per second per megaparsec. The cosmic microwave background from the early universe says 67. The 8% gap, the Hubble tension, has persisted through better instruments, better calibrations, better data. Either one method is systematically wrong, or there's new physics waiting to be found. In March, researchers at the University of Illinois and the University of Chicago published a new approach. They used the faint cosmic hum produced by every black hole merger that has ever occurred across the entire history of the universe. Billions of mergers, individually unresolvable, but collectively generating a background of gravitational waves that permeates all of space. The stochastic gravitational wave background. The key insight: if the universe expands slowly, observable volume is smaller, black hole mergers are packed tighter, the hum is louder. If it expands fast, larger volume, fewer mergers per unit volume, quieter hum. The background hasn't been directly detected yet, but its absence at certain levels already rules out some slow expansion scenarios. The full measurement is expected to be possible within 6 years as detectors improve. Number 16, because it's a proof of concept for a genuinely elegant tool. But the measurement itself hasn't happened yet. Number 15, a comet reversed its own rotation, and physics said it couldn't. It's about 1 kilometer across, 3 times the height of the Eiffel Tower. And it used to spin in one direction, then it stopped, then it started spinning the other way. Comet 41P Tuttle-Giacobini-Crassac is a Jupiter family comet that visits the inner solar system every 5.5 years. In March 2017, astronomers measured its rotation period at about 20 hours. 2 months later, 46 to 60 hours. It had slowed by a factor of 3. Then, by December of the same year, Hubble caught it spinning again at 14 hours, but in the opposite direction. David Jewett at UCLA, the astronomer who discovered the first Kuiper Belt object beyond Pluto, published the analysis in March. His explanation: gas jets escaping from the comet's surface act like tiny thrusters. When they're distributed unevenly, they create cumulative torque that pushes against the rotation. The comet slowed to near zero, the jets kept pushing, and they drove it into reverse. This is the first time a spin reversal has ever been directly observed in any comet. The continued rotational stress puts the nucleus under increasing structural strain. DeWitt predicts the comet will self-destruct in geological terms. Its current orbit gives it about 1,500 years before it breaks apart. Number 15, because it's a genuine first, a physical process predicted but never caught in action. Number 14, something from space hit a German house and nobody saw it coming. Right 1855 local time on March 8, a very bright fireball streaked across the sky above Western Europe. Belgium, France, Germany, Luxembourg, the Netherlands, thousands of people saw it. 6 seconds of brilliant light, then it fragmented. A fragment punched a football-sized hole through the roof of a house in Koblenz, Germany. Nobody was hurt. ESO's planetary defense team is investigating. But here's the uncomfortable part of this story. Nobody detected the object before it arrived. It came from the direction of the sun, the daytime side of the sky. Current sky surveys scan the night sky. Objects approaching from the sunward direction are invisible to our detection systems until they're already inside our atmosphere. This is called the Planetary Defense Blind Spot. ESA acknowledged it explicitly. The Chelyabinsk event in 2013, a 20-meter object that injured 1,500 people, also came from the sunward direction, also undetected. The Koblenz object was only a few meters across. Even with perfect detection, there was nothing to do. But the question remains, what if it had been larger? Number 14, because nobody was harmed and the object was small, but it demonstrated, in the most literal way possible, that our planetary defense shield has known gaps. Number 13, Hubble accidentally watched a comet dissolve. In November 2025, astronomers pointed Hubble at Comet C-SOAR 25 K1 Atlas. They wanted to study its coma chemistry. What they got instead was something they'd never seen before. The comet was breaking apart in real time. 3 days of Hubble observations caught at least 4 distinct fragments, each surrounded by its own coma. One of the smaller pieces broke up further during those same 3 days. The fragmentation had started about 8 days before Hubble's first observation. The team had scheduled these observations for completely different science. They had no idea what they were flying into. The odds of that happening while Hubble viewed the comet are extraordinarily minuscule, the team wrote in the paper published in March. Comets fragment from close solar encounters all the time. The intense heat at perihelion vaporizes ices, builds internal pressure, cracks the nucleus. K1 passed inside Mercury's orbit in October 2025. What makes this capture special is timing. Most fragmentation events are discovered after the pieces have already drifted far apart. Hubble looked at exactly the right moment to see a comet in the act of coming apart. Number 13, because it was an accident, and some of the most revealing observations in science are the ones nobody planned for. The top 10 starts now. On the night of March 2nd into the 3rd, the moon turned red. A total lunar eclipse swept across the Americas, Asia, Australia, and New Zealand. Totality lasted 59 minutes. The moon sat completely within Earth's shadow from 11:04 to 12:03 UTC. At its peak, the only light illuminating the lunar surface was the reddish glow filtered through every sunrise and sunset on Earth happening simultaneously. Every dust particle, every molecule of atmosphere-bending light around our planet, all of it concentrated and cast onto the moon's face. From the eastern coast of the United States, observers could see the moon and the rising sun simultaneously on opposite horizons. A phenomenon called a selenialion, geometrically impossible by strict calculation, made real by atmospheric refraction bending light around Earth's curve. The moon was technically below the mathematical horizon, but visible due to the bending of light through the lower atmosphere. And here's what makes March's eclipse meaningful beyond its beauty. This was the last total lunar eclipse visible from Earth until December 31st, 2028. Nearly 3 years. If you missed this one, you'll be waiting. Number 10, because the best astronomy content isn't always the most technical. Sometimes a billion people look up at the same red moon, and that moment matters. Number 9, 11 billion years ago, two galaxies collided. The collision fired a natural laser that we just detected. There are only about 109 known cases of hydroxyl megamissers in the entire universe. In March, a team in South Africa doubled the distance record for detecting one by nearly 2 billion light years. A maser is like a laser, but for radio waves. In space, megamasers form when two gas-rich galaxies collide. The collision compresses enormous clouds of hydroxyl molecules, water with one hydrogen atom stripped away. And the resulting pressure and infrared radiation pump those molecules into excited states, causing them to emit coherent radio waves in perfect lockstep. The result is 10 million to a billion times brighter than ordinary galactic masers. Using the MeerKAT telescope's 64 dishes in the Northern Cape of South Africa, a team led by Dr. Thado Manamela detected a megamaser at redshift 1.027, 11 billion light-years away. The universe was less than half its current age when this light was emitted. A foreground galaxy between us and the source amplified the signal about 10 times through gravitational lensing. "We are seeing the radio equivalent of a laser halfway across the universe," said Manamela. "We don't want to find just one, we want to find hundreds to thousands." MeerKAT will be incorporated into the square-kilometer array when complete, 50 times more sensitive than any existing radio telescope. The megamaser catalog is about to grow dramatically. Number 9, because of its poetry, an ancient galaxy collision fires a radio laser for 11 billion years, crosses the universe, and lands on 64 dishes in the South African desert. That's a good story. Number 8, the strangest planet in the known universe just defeated the most powerful telescope ever built. Take 5.5 Earth masses. Give it the radius of nearly 10 Earths. Calculate the density. You get 0.038 grams per cubic centimeter. Cotton candy is 0.01 to 0.05. This planet is, density-wise, sponge sugar. Kepler 51d is a superpuff planet, one of fewer than 15 confirmed in the galaxy. It orbits a young star 2,600 light-years away in Cygnus, alongside 2 other superpuffs. The entire Kepler 51 system is a collection of impossibly fluffy worlds that no current formation theory can satisfactorily explain. In March, JWST turned its NIRSpec instrument toward Kepler 51d for 14 continuous hours. The planet's enormous atmospheric scale height should have made reading its atmosphere straightforward. JWST saw nothing, a completely featureless spectrum across the full infrared range. The reason? A haze layer so thick and so high in the atmosphere that starlight passing through during transit never reaches the molecular layer beneath. The haze absorbs across all observed wavelengths. It may extend for roughly 6,000 kilometers, comparable to Earth's entire radius. A planet-scale blanket of photochemical fog. Lead author Jessica Libby Roberts, these ultra-low-density superpuff planets are rare and they defy conventional understanding of how gas giants form. Even after Webb, Kepler 51d remains a mystery. Number 8, because it's not just a puzzling planet, it's a demonstration that even our most powerful telescope has hard limits. Number 7, 6 days from now, humans will leave Earth for the Moon. When the March 26 episode aired, there were 6 days left until launch. Net, April 1st, 2026, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen would strap into Orion and leave Earth's orbit. For the first time since Apollo 17 in December 1972, 54 years. The mission is not a landing, it's a systems demonstration. Artemis II follows a free return trajectory. The physics of the path itself brings the crew home even if the main engine fails. They'll pass within 5,500 miles of the lunar surface, swing around the far side of the moon. 4 minutes of complete communications blackout, completely isolated from Earth, and ride the arc back. At their farthest point, the crew will be 280,000 miles from Earth, breaking Apollo 13's record of 248,000 miles set in 1970. Jeremy Hansen becomes the first Canadian to travel to the moon. Victor Glover becomes the first black astronaut to fly beyond low Earth orbit. The SLS stack rolled to pad 39B on March 20th. The crew entered quarantine March 18th. Everything was go. Number 7, because the mission launched in April, not March, but the rollout, the quarantine, the countdown. March was when it became real. Number 6, a star vanished in the Andromeda galaxy. JWST just photographed what's left. In 2014, something brightened in the Andromeda galaxy. An infrared brightening over 2 years. Then it began fading. By 2024, the source had dropped to just 7% of its original luminosity. No explosion, no supernova, just gone. In March, astronomers published JWST and Chandra X-ray observations of what remains at those coordinates. JWST detected a very faint, extremely red object consistent with a thick dust cocoon surrounding a newborn black hole. Chandra saw nothing at X-ray wavelengths, detecting limits 100 times deeper than the infrared, and still nothing. Which is exactly what you'd expect, a black hole accreting material surrounded by dense dust that absorbs every X-ray before it can escape. The mechanism is a failed supernova. The star's core collapsed. Neutrinos burst outward, but the shock wave was too weak to eject the envelope. Instead of exploding, the star folded inward. About one solar mass of outer material escaped at low velocity, cooled, and formed the dust shroud. The dust is expected to thin enough for X-rays to break through in about 27 years. Researchers estimate that 10 to 30% of massive stars may end this way, not as spectacular supernovae, but as quiet disappearances. We've only confirmed two candidates. IMS 31 2014 DS1 in Andromeda, at only 2.5 million light-years, is the closest ever observed. Number 6. Because watching a star silently become a black hole at Andromeda distances is extraordinary. But it's still a candidate. Confirmation comes in decades. Top 5. These are the stories that defined March 2026. Every rocky exoplanet JWST has studied closely. The TRAPPIST worlds 55 Cancri showed either no atmosphere or a negligible one. March changed that record. TWI 561b orbits its star every 10.5 hours, 1 full year every half Earth day. It sits at 1/40th the distance that Mercury orbits our Sun. Its surface should be around 2200 degrees Celsius, hot enough to vaporize rock. JWST observed it for 37 continuous hours, nearly 4 full orbits. The measured dayside temperature came back at about 1800 degrees. That 400-degree gap is the discovery. A 400-degree gap means something is moving heat from the sunlit side to the night side. An atmosphere. A thick one. On a world where no atmosphere should have survived. The reason it persists, the surface is a global ocean of molten rock, a magma ocean thousands of kilometers deep, continuously releasing volatile compounds into the atmosphere through outgassing. The atmosphere partially erodes from stellar wind. The magma replenishes it, a dynamic equilibrium that has apparently maintained this cycle for 10 billion years, longer than our own solar system has existed. Lead author Johanna Teskey at Carnegie Science. It's really like a wet lava ball. Rocky planets hold on to atmospheres. Ancient, molten, volcanic rocky planets hold on even when they shouldn't. This directly changes what we expected from wet rocky planet science, and it opens the question of what other hostile worlds might quietly maintain atmospheres in ways we haven't predicted. Number 5, because it rewrites the expected results of an entire class of JWST observation. Number 4, for 45 years, textbooks described how stars spin. In March, all of them were wrong. Stars spin like washing machines, the equator faster, the poles slower. Our sun's equator rotates in about 25 days. The poles take 35. For 45 years, the accepted theory predicted that as stars age and slow down, this pattern would eventually flip. Poles faster than equator, the anti-solar rotation model. It was developed in the early 1980s, confirmed by numerous subsequent computer simulations, and became established stellar physics. Not once in 4 decades of observing actual stars did anyone ever see it happen. Every old, slow-rotating star that was measured showed solar-like rotation, with the equator still faster. The theory and the observations disagreed. Nobody knew why. In March, Hideyuki Hata and Yoshiki Hata at Nagoya University published the answer. They used Fugaku, Japan's most powerful supercomputer, to simulate a star at 5.4 billion grid points. Previous simulations used orders of magnitude fewer points. And at lower resolution, something critical vanishes from the mathematics: magnetic fields. At low resolution, the simulated magnetic fields weakened artificially, became insignificant noise. With them, effectively gone from the math, the simulations produced the predicted rotation flip. At Fugaku's resolution, the magnetic fields remained strong and persistent, and the finding, magnetic fields, working together with turbulent plasma motions, prevent the rotation flip throughout a star's entire lifetime. The equator never stops outrunning the poles. So even though stars do slow down, the switch doesn't happen because magnetic fields, which previous simulations missed, prevent it. 45 years of theory built on simulations that were accidentally erasing a physics effect by not having enough resolution to capture it. Number 4, because overturning half a century of stellar physics with a higher resolution computer simulation is exactly the kind of result that takes the field years to fully absorb. Number 3, two objects found each other 900 million light-years away, and when they merged, they broke the rules of orbital mechanics. On January 5, 2020, LIGO and Virgo detected gravitational waves from a merger 900 million light-years away. A black hole of roughly 9 solar masses colliding with a neutron star of about 2. The first robust detection of this type of merger ever recorded. Scientists published the results, filed it in the catalog, and moved on. Then, in March 2026, a team at the University of Birmingham reanalyzed the same signal using a new waveform model. One that, for the first time, could simultaneously handle both orbital eccentricity and spin precession. They found something the original analysis couldn't see. The orbit wasn't circular. It had an eccentricity of 0.145, a measurable oval. Circular orbit was ruled out at 99.5% confidence. Here's why that's remarkable. As two compact objects spiral toward each other over millions of years, gravitational wave emission drains energy from the orbit, making it progressively more circular. By the time two objects are close enough for LIGO to detect, the final fraction of a second before merger, the orbit should be essentially a perfect circle. Eccentricity should have been radiated away long ago. To have an oval orbit survive to the merger, something must have perturbed the system relatively recently in astronomical terms. The system almost certainly didn't form from two stars born together in isolation. That pathway produces circular orbits. Instead, it likely formed in a dense stellar environment, a globular cluster or nuclear star cluster, where gravitational interactions with nearby stars can inject eccentricity into a binary late in its evolution. During Pratt at Birmingham, the orbit gives the game away. Its elliptical shape just before merger shows this system did not evolve quietly. Number 3, because this rewrites the formation story of an entire class of gravitational wave events, and opens orbital eccentricity as a new diagnostic tool for understanding where and how these systems are born. Number 2, and then there's the story of our sun. The center of our galaxy is not a hospitable place. Gamma ray bursts, outbursts from the supermassive black hole at its core, dense stellar crowds that can destabilize planetary orbits. Supernova rates orders of magnitude higher than the outer galaxy. 4.6 billion years ago, our sun formed inside all of that, at roughly 5 kiloparsecs from the galactic center. Today, we're at 8.2 kiloparsecs, about 27,000 light-years from the core. The sun migrated more than 10,000 light-years outward, from the dangerous inner galaxy to the quiet suburban disk. And somehow, after that migration, life emerged. In March, 2 companion papers using data from ESA's Gaia telescope cataloged 6,594 solar twins. Stars nearly identical to our sun in temperature, surface gravity, and chemical composition. 30 times larger than any previous solar twin dataset. The age distribution of those twins told a story. The sun's cohort, stars aged 4 to 6 billion years, clustered around similar galactocentric distances as our sun. They made the same journey. The sun didn't migrate alone. It was part of a mass exodus of thousands of solar siblings. Previous simulations suggested only about 1% of stars born at the sun's birth radius could cross the corrotation barrier, a gravitational fence created by the rotating bar at the galaxy's center, and reach the outer disk within 4.6 billion years. 1% would make the Sun a statistical anomaly. 6,500 solar twins at similar positions say it wasn't an anomaly. The galactic bar was still forming when this cohort migrated. The fence wasn't fully built yet. A window opened for a brief geological instant, and thousands of stars escaped together. And here's the implication that makes this number 2. The migration happened 4 to 6 billion years ago. Life on Earth appeared about 3.8 to 4 billion years ago. The Sun reached its current stable orbit just before life began to emerge. The quiet, low-radiation, gravitationally stable environment of the galactic suburbs, where complex chemistry could persist for billions of years, may be the reason you're listening to this right now. Number 2, because the implication isn't just about solar system history. It's about the preconditions for Earth and for us. Number 1. On November 12, 2005, at 15:18:45 UTC, all 4 gravitational wave detectors on Earth registered a signal simultaneously. LIGO Livingston, LIGO Hanford, Virgo in Italy, KG Ray in Japan. The signal was designated S2511 12 centimeters. The analysis paper was published in March 2026, which is why it's here. The chirp mass of the merging objects, a weighted average derived from the waveform, came back between 0.1 and 0.87 solar masses. More than 99% probability at least one of the objects weighed less than our Sun. That number is the entire story. A stellar black hole forms when a massive star's core collapses. The absolute minimum for this process is roughly 5 solar masses. Neutron stars, the densest known stable objects, have a minimum mass of about 1.4 solar masses. There is no known astrophysical process, no stellar evolution pathway, no mechanism in modern physics that produces compact objects with masses below 1 solar mass. None. Except one theoretical process developed 50 years ago. Stephen Hawking spent the early 1970s developing the mathematics of primordial black holes. Objects that formed not from stellar collapse, but from random density fluctuations in the first 10 to the power of -24 seconds after the Big Bang, before any star existed, before any galaxy formed. Ultra-dense pockets of energy and matter collapsing under their own gravity in the first cosmic instant. Hawking published the foundational mathematics in 1971 and 1974 alongside Bernard Carr. The theory has existed for 50 years. In that time, astronomers have searched for primordial black holes through Hawking radiation, gravitational microlensing, and pulsar timing. LIGO detected over 300 gravitational wave events from 2015 to 2025, all from stellar mass objects. S251117 SABR's Calat, the solar candidate ever recorded. The paper's lead author, Nico Capelluti at the University of Miami, wrote, "The most plausible explanation for the LIGO signal, which lacks any conventional astrophysical explanation, is the detection of a primordial black hole." Now, the caveat: the false alarm rate for this event is estimated at once every 4 to 6 years. That's too high to claim a confirmed discovery. Christopher Barry at LIGO said explicitly, "For an event this unusual, the estimated false alarm rate is too high to claim a discovery." This is a candidate, an extraordinary one, but a candidate. The next LIGO observing run begins in September 2026. If primordial black holes are real at detectable masses, we should see more. But here's the full scope of what we're talking about. Primordial black holes are a leading candidate for dark matter, the 85% of all matter in the universe that we cannot see, cannot touch, and cannot explain with any known particle. If black holes from the first microsecond of the universe exist at subsolar masses, they could be woven through every galaxy holding them together. The paper that Hawking wrote before most of our listeners were born might be describing the majority of matter in the universe. A signal from 900 million light-years away, from the final moments of 2 objects whose masses fit no known astrophysical process, traveling to 4 detectors on Earth on a Tuesday in November. That's number 1. That's the story of March. That was March 2026 in space. A comet reversed its own spin, the first time ever observed. A star in Andromeda quietly became a black hole without an explosion. The most energetic particle ever recorded traveled from a blazar on the edge of the visible universe to arrive at a detector 3 kilometers below the Mediterranean. A 45-year-old stellar theory was retired by a Japanese supercomputer. And a planet made of cotton candy density defeated the James Webb Space Telescope. And somewhere in the LIGO data from November 2025, a signal weighing less than our sun, a signal that cannot be explained by any known astrophysical process, is waiting for the September run to confirm what it might be. We'll be back next month with April's Top 20. More missions, more discoveries, more moments where the universe reminded us how much we still don't know. This is Stardrift FM. Thanks for tuning in.